Hi everyone, so this should be the first video that you watch in this class in Chem 2. So the way that these videos are going to work is that I split them up into like little topics of the chapter, and then usually at the end or like midpoint, depending on the topic and how long the video is, I will have exercises that we will go through together. In the slides that I post on PowerPoint, those will have extra exercises. So those I label them on your own. So I expect you to hopefully at least attempt them on your own, and then we go through them together during our weekly online session, like live session, which is optional, but hopefully you can make it. And the time will be determined based off the survey results from the quiz. But that's basically how these videos will work. Other than that, I want to welcome you to this class. You've probably read all my announcements, many announcements, right? And I mean, let's get started. So in this class, we are continuing off where we left back in Chem 1. We left off talking about gases, and we did talk about solids and liquids, like the very basic stuff at the very beginning of the class. But we're going to continue that on, and we're going to talk about solids and liquids. So we're going to talk about the interactions that these, the molecules of these have, and how it affects bigger, larger physical properties. So some questions that I hope you can answer at the end of this semester is, for example, why is propane a gas while isooctane is a liquid? So the reason I bring these two up is because they're both hydrocarbons. So the major difference between them in terms of like what makes them up is that isooctane is bigger, but they're both hydrocarbons, so they're both composed of nothing but carbons and hydrogen. So why is isooctane being bigger? Why does that translate to it having a different state at room temperature? So just to review really quickly, the basic properties of solids, liquids, and gases. Solids, the particles, so by particles we mean either atoms, molecules, or ions, any of those. They are in fixed positions, but, and we didn't mention this in Chem 1, but the particles actually vibrate. They don't move around. They're in a certain position, but they are vibrating, so there is a tiny bit of motion to them. In a liquid, the particles move past each other, but they're always in contact with each other. And in a gas, they're just completely like antisocial. Like they're just moving around, doing about whatever they want. They hit the container, they hit the sides of the container. They can collide with each other, but you can just think of them like they're constantly moving. So now we're going to quickly review kinetic energy. So we learned about this way back in the thermochemistry chapter, which was chapter 5 in Chem 1. And there's three things you should take away from this particular slide: kinetic energy, thermal energy, and temperature. So kinetic energy is the energy associated with motion. A lot of you probably have some idea about kinetic. You've heard this word before, hopefully. And yeah, it's associated with motion. Now, in terms of what that means for chemistry, for particles, which again, particles are either molecules, ions, or atoms, that means that the faster your particles are moving, then the higher the kinetic energy. Now, thermal energy is a form of kinetic energy, and thermal energy is associated with temperature. So you see how these are all kind of connected. So the higher the kinetic energy, the higher the thermal energy, and then the higher the thermal energy, the higher the temperature. So the more motion that your molecules or particles have, the higher the temperature. So now that we've talked about kinetic energy and we've reviewed that, we can start talking about intermolecular forces. So that is the main topic specifically about this video. And they're exactly what they sound like. So between molecular molecules, and forces are like attractions. So the relationships that I want to help establish for you is that as you increase intermolecular forces, then you will start going from gas to liquid to solid. So solids have the most intermolecular forces, so that's what's holding them together at a certain temperature. Now, if you want to overcome those intermolecular forces, you're going to have to increase the kinetic energy, in other words, the temperature. So think about how you have ice, solid like ice, solid water. As you increase the temperature, so you take the ice out of the freezer, it's going to turn into a liquid. Let's say you took that water, liquid, you put it in a pan and you put it over the stove. You would be increasing the temperature even more compared to room temperature, so then that would turn it into a gas. So as you increase intermolecular forces, you go from gas, liquid to solid. As you try to overcome these intermolecular forces, you're going to have to increase the temperature. So to illustrate those different states and how it correlates with the temperature, so the kinetic energy, think about here in Texas, the great state of Texas. We have like the most humid atmosphere ever, right? Or at least it feels like that. And basically it's because it's so hot that water turns into vapor and just hangs around. And think about how whenever you have like a cold glass of soda or something and you're outside in the hot, the temperature is decreasing, so the kinetic energy is decreasing. So you can't overcome those intermolecular forces. So what happens is the water vapor starts condensing on wherever that cold is. So you start getting water droplets on the outside of your glass. So why are molecules even attracted to each other in the first place? Like, why do IMFs even exist? And it has to do with something that we've already learned. We learned in Chem 1 about ionic compounds and how ionic compounds are made up of a cation and an anion. So cations are positive, anions are negative. And we see in those compounds that they have an attraction to each other because of that positive and negative. And it also has to do with electrons, but again, it has to do with those charges. So basically the laws of physics, they show that positive is always attracted to negative, and it's exactly what happens in compounds. So not all compounds have those like polar charges the way that cations and anions do, but molecules can have dipole moments. So we're going to go into that, but basically this is what causes those attractions. And some things that I want you to understand is that the larger the charge, the stronger the attraction. The longer the distance between the molecules, the weaker the attraction. So in intramolecular force, so intra means within a molecule. So it's talking about a bond. In intermolecular forces between two different molecules. So just so you get that terminology. Just so you don't get it mixed up. So again, here we have some more review from Chem 1. So polar bond, if you don't remember what that is, it's a covalent bond where you have two nonmetals. That's what covalent bonds are, only between nonmetals. And you have a large electronegativity difference between the two. So one of the atoms will like to hog the electrons towards it more than the other one. So what you end up having is like covalent bond, right? They're sharing electrons, but it's actually not equal. A dipole moment is caused by that separation of charge. So you have one atom hogging electrons more, meaning it's going to have more negative charge towards it. So that's going to cause a separation of charge, which causes a dipole moment of that bond. Now, in order for a molecule to be polar, you have to have two criterion, I never know the difference. You have to have these two, specifics to it. You have to have polar bonds, and you have to have an unsymmetrical, also unsymmetrical, asymmetrical, I don't know. You have to have an unsymmetrical shape. And the reason for this is if we look at, for example, CO2. CO2 has two polar bonds, right? Each carbon to oxygen bond is polar, but when you look at the vector addition to this, and this is math and physics, which I don't want to get into. I just want to present it the easiest way possible. But think of it like a tug of war. So each of these oxygens on each side of the carbon are pulling electrons towards it. And because they're the exact same atoms and they're the exact same double bond, they pull equally actually. So it ends up canceling each other out. So that's how I want you to think of vector addition as like a tug of war. And for example, HCl, it doesn't have anything canceling out because it's just the chlorine pulling and hogging the electrons away from the hydrogen. So it ends up being a polar molecule versus carbon dioxide is not a polar molecule, but it does have polar bonds. So in this slide, I'm showing you, first of all, some molecular geometries where if you have nothing but polar bonds on them and they're all the same type of polar bond, these molecular geometries will cause those polar bonds to end up canceling each other out. So you'll end up having an overall non-polar molecule. So look at their shapes. They all have some sort of symmetry to them. So for example, square planar, it's one of our molecular geometries. It's a derivative of our octahedral electron geometry. And if you have this shape and you have the same exact types of bonds for all of them, you're going to end up having an overall nonpolar molecule because they're all pulling equally. So just imagine that they're all pulling, like, let's say, again, a tug of war. They would all cancel each other out. And the same thing with everything else. So this trigonal bipyramidal, first you have your equatorial positions. They all pull in their own way, 120 degrees away from each other. And then you have these two linear that pull up and down. Tetrahedral is also symmetrical. If you keep turning it around, you'll keep having the same shape over and over. Linear is easy to see. It's just like our CO2. Trigonal planar is also easy to see. It's like pulling in a triangle shape. And then octahedral, you can also see that you have those four and then the top and the bottom. So on top over here, I have a diagram showing a bunch of different molecules and how they're different and how some have overall net dipoles versus other ones don't. So when something has a net dipole, that means it's an overall polar molecule versus when something does not have a net dipole, for example, this one right here, that means it's nonpolar. And if you actually look at it and like determine the molecular geometry, you'll find that it's one of these shapes over here.